Thank you, Leticia. So I'm very grateful for the organizers for setting up this program, this conference, and to invite me to present this work. So what you're staring at here, this red line, is a non-analytic potential, all right? It has a kink at phi equal to 0. And the main message of my presentation is that while this object will never happen in equilibrium, field theories, it can actually develop out of equilibrium and modify drastically the infrared physics of field theory. So as you can see, there is still a question mark on my title, and because this story is still under development. So I've been working on this in the past couple of years with the collaborators Claudio Chamon and Manas Kulkarni. All right, so before we go non-equilibrium, let me quickly review the Ginsburg-Landau approach to constructing effective field theories in equilibrium. As you know, that's a really pillar of modern physics because it classifies all equilibrium phases of matter into a single common framework. So the game is to first, you have a many-body system. You want to first identify your order parameter, understand under which symmetry group it transforms, say in the disordered regime, count your dimensions, 1, 2, 3, 4 dimensions. And then you may then classify your model as a member of a universality class, which basically tells you everything about the IR, the infrared properties of your system. So for today, I'm going to work specifically with the ON models, and in particular the Ising class, so n equal to 1, the ON symmetry n equal to 1, which encompasses magnets, liquid gas, binary mixtures, etc., etc. All right, so let me refresh your memory by illustrating how it works. So let's take this very simple Ising model with a Z2 up-down symmetry. And here it's represented in 2 dimensions, and it's contact with the thermostat. And to capture the essence of the magnetic transition between paramagnetic and ferromagnetic phases, the key idea of Landau is to elevate this order parameter, which is magnetization in that case, to the rank of a fluctuating field, all right? So instead of working with magnetization S, you work with a field phi of X, all right? And instead of working with the Gibbs-Boltzmann measure, which involves the Hamiltonian of your spin system, you are now going to work with a free energy functional, a Landau free energy functional, F of phi, all right? And because we're working here with the Ising model, you all know that the corresponding theory is the lambda phi 4 theory. Right, it's written here. So you have a gradient phi square, mass phi square, and the lambda phi 4 term. Right, that's also called sometimes the Ginsburg-Landau-Wilson model. Right, so and in general for generic model, for generic systems, Landau gives us a very simple recipe to construct this free energy density, which is very elegant and which is really not costly at all. He's telling us, look, guys, you should just invoke the 4 following principles, which are locality. The free energy should be an integral of the space of the free energy density, the density that is a function of the field phi and maybe the first gradients of phi. You should have all the symmetries of your microscopic model should be built in. So for instance, here we have the Z2 symmetry translates into even energy density functional phi goes to minus phi, right? There is this even symmetry. You have also translation invariance, which is built in. Then he's telling us, well, it should also be analytic. So the free energy density should be analytic in the field and the first gradient of the field. So this expansion in powers of phi is involving integer powers of phi. So phi square, phi 4, etc. And maybe to finish, a stability rule that tells us that you should have a confining potential, which makes your theory stable and which makes your math also stable, defined. And after you have built this free energy density, if you want for a full meal into the infrared physics, you can take this goodness and basically cook it in the RG pot, and the RG will tell you ultimately which of the terms you can keep and which of the terms you can discard. And this is the question of relevant terms versus irrelevant terms. All right. And this, of course, depends a little bit on dimensionality. But I would like to emphasize that even before doing this RG step, which is usually, you know, considered as the heart behind the universality and equilibrium, even before the RG step, these rules are very constraining. You know, there are not so many free energy densities you can write given dimension, given a set of symmetries, and especially given this rule of analyticity. Look, you have this phi squared term here, and the next term that can come because of symmetry and analyticity is the phi 4 term. So there is kind of a distance between this phi square and phi 4, which if you didn't have any analyticity rule, you can in principle put some phi to the absolute value of phi to the 2.7 in the middle. And then the battle for critical phenomena, IR physics, would not be a battle between this power 2 and this power 4. It would be a battle between this power 2 and maybe the power 2.7 in the middle, right? So the fact that, you know, ultimately you have universality is kind of protected by this analyticity rule, all right? That prevents you to write, that prevents you basically to be eccentric in what you write down here. And ultimately, you know, this battle between power 2 and power 4 is going to, of course, condense into this critical exponent that you can measure, you know, at criticality. So that was a quick review. And for us now, the question is whether we can extend this framework to non-equivalent physics, to non-equivalent phase transitions. And people have already challenged the principle of locality which is behind, and in principle you don't expect much locality out of equilibrium, especially if you have currents. People have considered also to break symmetries like the equilibrium detail balance symmetry. And what I'm challenging today is this rule of analyticity, right? And I will do it in some corner. I will not do it in the full generality for any out of equilibrium state. I will consider non-equilibrium steady state, so those states that are non-equilibrium but still time translation invariant, right? And I will even work in some subclass of non-equilibrium steady states, those who are isotropic, homogeneous, and without any current threading through the system. So let me give you two examples of what I have in mind. On the left-hand side here, you have a simple Ising model which is coupled to two different baths at two different temperatures and maybe two different energy spectra. So this is going to drive this Ising model out of equilibrium, and it's going to reach non-equilibrium steady state. And another model which we introduced, which is the stochastic reheating Ising model, where your Ising model is coupled to also a thermostat at temperature T, but randomly at random times, the system is going to be reset to disordered state, right, to infinite temperature state. With a rate R. So we call it the random bomb, random thermal bomb, right? And you can convince yourself that those systems, they're out of equilibrium, and eventually they're going to reach a non-equilibrium steady state. So some stationary distribution for the magnetization field, right? Finesse, that is there. And you can always define, if you want, an effective free energy by just taking the log of this distribution function, right? So this defines this non-equilibrium steady state free energy, f of phi, which of course, the game now is to understand what are the basic principles that are guiding us and to write it down in a heuristic manner, the way that Landau is doing in equilibrium, right? And I'm going to argue that we have to revisit the claim of analyticity. Right. Okay, so let me start with the two-bath Ising model as an appetizer. To compute the non-equilibrium steady state, I will resort to mean field theory, mean field approximation, because then it's very easy to write down the self-consistent equation for the field phi, which involves the temperature of the two baths, T1 and T2, and which also involves the spectra of the two baths, mu1 and mu2. There are two functions of the energy. We call them hybridization function. But basically, they tell us about the energy structure of the environment, right? And of course, if you were to work in equilibrium, say you put the temperature T2 is equal to T1, then the self-consistent equation that you see here would but simplify to just phi is equal to tang phi over temperature, the usual set consistent mean field that you get with the bias field, right? Here we're out of equilibrium. We can go directly to the steady state, and this is the equation you get, and you can elevate it to the rank of a free energy, an effective free energy functional f. And what you see if you contemplate the operator content of this free energy is that you recognize the phi square and the phi 4 guys that were there because of we're describing Ising physics. But in the middle, you have these new terms, absolute value of phi to be alpha, where alpha can or cannot be integer depending on what you have, where alpha comes from the low energy structure of your baths. Basically, it comes from the low energy limit of this hybridization function when the energy is small. Why is it that we're looking at small energy? Because we're looking at things close to criticality when phi is close to 0. And you have a prefactor here that of course vanishes whenever you're back to equilibrium. So the main message here is that just mean field approximation, very simple models. You can show that the phi 4 theory is being deformed by new operators that are intrinsically out of equilibrium. They are not there if you're in equilibrium, and that are non-analytic because this absolute value of phi to some power is of course non-differentiable at phi equal to 0, right? And as I said before, now that you have this phi alpha that can live in the middle of phi square and phi 4, the battle for criticality is now a battle between the phi square and the phi alpha, right? So it will change in particular your critical exponent. Okay. So that's the first part of my story, and that was made by just mean field analysis, and we did it here on a simple model, but you can work with different models and convince yourself that typically non-equilibrium environment can bring in some non-analyticities in the free energy function. But now we only discuss things within the mean field approximation, and it means basically with the saddle approximation, assuming that the field is constant, we neglected the fluctuations, and important questions are in front of us. So the first question is this story surviving away from the mean field approximation? Or in other words, is there an upper critical dimension above which the fluctuations are indeed irrelevant and mean field is actually exact? Second question, is this story surviving in infrared, right? As you zoom out, as you go to lower and lower energies, if you coarse grain on larger and larger scales, so more mesoscopic level. And third question, is the story of non-analytic operators surviving the fluctuations, the stronger fluctuations that you get typically in low dimensions, I mean in dimensions lower than the upper critical dimension. All right. So to discuss these three field theoretic questions, I will introduce a relatively simple model where these three questions can be framed and answered both analytically and numerically without much, without being too hard to solve. This is again this around stochastic reheating Ising model. All right. So again, it's simple Ising model connected to a thermal bath, and from time to time with rate R, you're being reset to infinite temperature or disordered state. Right. And the reason why we can solve for the non-equilibrium steady state of this type of model is because there is a very nice formula, which is called the Renewal Formula, which is basically a dictionary between the non-equilibrium steady state of this physics here, so that's the stationary measure for our problem, to the Laplace transform of the probability distribution for the magnetization of another problem, time-dependent problem, the problem of just a single Ising model following a quench without any resetting, without any reheating, random reheating, right? So this physics here on the right-hand side is the physics of Ising model after a quench from infinite temperature. So that's basically the well-known physics of coarsening, which Laetitia and many other people have worked on, right? And luckily for us, we know a lot about this physics. We know in particular how to write down the field theory. The dynamics are in particular, you can write them down by means of the model A stochastic equation. So it gives you an equation of motion, stochastic equation of motion for your magnetization as a function of x and t, which involves the free energy and involves some stochastic noise. the initial condition at n equals to 0 is 0 because you start from infinite temperature, so from a paramagnetic solution. And I'm insisting that this free energy that is entering here, this model A dynamics, is the equilibrium free energy. So we're back to the equilibrium lambda phi to the 4 theory, which we well know, and we know in particular how to do the RG there. And if we know how to do the RG here, we know how to do the RG here, we know to do the RG here, and we know to do how to do the RG for our random stochastic heating problem, right? And this is what we're going to do. And whenever you can neglect the fluctuations, say that there is indeed, well, and first, because of this dictionary, if there is upper critical dimension there, it has probably to be the same as the upper critical dimension for this problem. So the Ising model after a quench, which we know is the same as the equilibrium problem, which is equal to 4. So we can already conjecture that the upper critical dimension for our problem will be equal to 4. And we can think that above equal to 4, we can comfortably neglect the fluctuations and work with basically Langevin equation of motion of a single particle in a quartic potential, which we also know everything about because we know how to do the RG, etc., etc. All right. Let's proceed. And let me quickly refresh your memory on what's happening in equilibrium. I'm sure you've all seen these things millions of times, so I will go quickly with the video. So I'm zooming out. I'm performing the real space RG here for my spin system. And what you see on the lower side, oops, everything is going at the same time, sorry. What you've seen on the lower side here is your normalization of your potential, all right? It was a quartic potential, and after zoom out, it went for an inverted parabola. Now we're above critical temperature, we're zooming out, and the potential is now becoming sharper and sharper, right? You're localizing your solution at the paramagnetic fixed point. And if you're exactly at criticality and you zoom out, what you're seeing is that your potential is becoming basically flatter and flatter. In all those cases, the potential is quadratic, whether an inverted parabola, a flat potential, or usually your typical parabola that gets sharper and sharper. All right. So because we know everything about equilibrium and we have this dictionary, which is the renewal formula, we can compute everything out of equilibrium and extract the non-equilibrium free energy density. And we can perform the RG into the infrared until the fixed point. And what we're getting is the following. So above the critical temperature, so T is the temperature of the bath, above the critical temperature, the non-equilibrium steady state is basically controlled by a universality of equilibrium Ising model. All right, so we're back to a quadratic potential, and that's it. But what's new is that below TC now, up below TC, you can compute the free energy potential, or here it's just a Landau potential, and you can stare and you can look at all the operator content. It's much different from what you have in equilibrium. Now you have also the phi 2 and phi 4 potential, but you have now terms like absolute value of phi, absolute value of phi to the 3, right? And this is really different from what you have in equilibrium at low temperatures. And this shows that these non-analytic operators that we have discovered in the mean field approximation scheme are now actually there, and they resist into the infrared. Okay, here we're at the fixed point. We computed exactly the non-equilibrium fixed point potential, and it shows this non-analytic potential, and they are the ones that are controlling the physics of fluctuation close to criticality. At phi equal to 0, this term is winning. All right. So in particular, this cast is really winning and is going to destabilize the usual Wilson-Fisher fixed point that is there in equilibrium. So the question number 2 was, does it survive infrared? And the answer is yes, it does survive infrared, this story. We have non-analytic operators that are there until the infrared fixed point, and they actually destabilized the equilibrium universality class that we all know. So that was the story for d equals 4. For dimension above the upper critical dimension, where we can work with Langevin instead of the full field. And we can also do numerics, and it's probably pointless to show you because it agrees perfectly with the analytics, of course. But the question now is the third question, whether or not this story survives the fluctuations that you have in low dimensions. And for that, we are not able to do the analytics, but we're able to do numerics. And the numerics, again, are going to be very simple because we're going to use this renewal formula. We're not going to do the numerics for the heating problem. We're going to do the numerics for the Ising model following a quench. We're going to do the statistics of the magnetization. So it's a time-dependent statistics that you compute on coarse graining boxes of size L times L. And you take larger and larger boxes. Then, out of these statistics, you use the renewal formula, and you obtain the stationary measure of the stochastic reheating Ising model. And then you take the log of this probability, and then you have your Landau potential, which you can extract numerically. And the results are qualitatively very similar to what we obtained before above z equals 4. And for above the temperature, the critical temperature, when you go into the IR, basically you see your parabola becoming sharper and sharper. So the plain line are the non-equilibrium steady state computed from the numerics, and the equilibrium lines are at dash points, right? And you see that they are almost on top of each other. And as you go into the IR, you have your potential that basically closes, and your field that lives there at phi equal to 0, which is the paramagnetic solution. Right? It's controlled by the equilibrium universality class. But now if you do it the same below the critical temperature, so the dashes are again the equilibrium lines. So you see your, in principle, you should see you're going to the IR from blue to red. You should see your quartic potential becoming a double well more and more, you know, with the wells that are more and more sharp. And this is there. I'm sorry. But if you look at the non-equilibrium steady state potential now, what you're seeing is totally a different story. You see that the Landau potential is now it has a cusp, and this cusp is becoming cuspier and cuspier as you go into the IR. Okay, you can actually measure things numerically. You can do some fits. You can convince yourself that this cusp is winning the battle, right? And that is going to control the IR physics there. So it's a proof that also in low dimensions, these operators do survive the fluctuations, and can actually be relevant. All right. So this answers the question number 3. So to summarize my work and what I presented to you, I have given you 2 concrete examples with non-analytic operators that appear in the free energy, the effective free energy. Typically, these non-analytic operators, they are intrinsically of non-equilibrium nature. They come from the non-equilibrium environment, right? They can be traced back to low energy features of the environment, typically. So maybe we can contribute in some sense of, maybe it could help into redefining universality out of equilibrium. They are not artifact of the mean field approximation, and it's pretty good news because it means that we can do mean field and be able to get, and mean field is cheap, and it's enough to detect those non-analyticities at a relatively low cost. These things can survive in low dimension. They can survive the fluctuations in low dimension, but most importantly, they can survive in the IR, and it means that they can be relevant in the RG sense, and it means that they can, in principle, destabilize the equilibrium fixed points that we all know, and take us to new non-equilibrium universality classes. All right. Thank you for your attention.
Thank you, Camille, very much. Thank you. So, yes, please, I have any questions. Oh, I have 4 raised hands, so please, who can be the first one? So, Tarun, you want to start?
Sure. Thank you for your nice talk. I have a basic question. So even within equilibrium physics, if one is coupled to a heat bath of some kind, one sometimes do work with non-analytic terms, because if you just integrate out the heat bath fully, including the low energy modes of the heat bath, you get non-analytical term. For example, in the standard Hertz-Millis treatment of itinerant fermions, you get a mod of omega term if you integrate out the electrons. So is the origin here similar, that you have some baths which you integrated out some modes which were essentially very low energy modes, which you shouldn't be. Anyway, we don't want to do that, but sometimes we have no choice. We end up doing that, and we get these extra terms, or is there something more to it than that?
No, I think so. In the first example, so the two-bath Ising model with two baths, indeed, the non-analyticity is just coming from the bath. So in some sense, typically you get non-analyticities out of taking some infinite limit, some thermodynamic limit somewhere, and it means that the thermodynamic limit has already been taken in the bath, and the bath is bringing the non-analyticity into the system, even though the system is not. So we're still working at the mesoscopic level. We're not in the IR yet, but still the bath has brought the non-analyticity into the system through this integration out of the bath. Indeed, yes.
So in that sense, it's not so much the non-equilibrium part. It's just the fact that you have integrated out some, because even within equilibrium, we do get such non-analytical terms if we integrate out.
That whenever you do that in equilibrium, there is something that typically, so I would need to see the Hertz-Nilis theory again, but my understanding was that typically if the bath is obeying detail balance, so if the bath is in equilibrium, because detail balance, there is a tangent, there is this exponential or this tangent or this fluctuation dissipation in the middle. My understanding was that it was preventing us from having any effect of the non-analyticity in the bath, but not transfer to the system.
No. I mean, that's not correct. I mean, yeah. I mean, you certainly had non-analyticity is what determines all the. I mean, it's mod omega plus k square. That's the propagator, and mod omega is not analytic, and that determines everything, all the critical properties. The fact that there's a mod omega there is crucial to determine, for example, the fact that the dynamical critical exponent is 2 or 3 depending on paramagnet, anti-paramagnet. So I mean, in any RG scheme, if I integrate out modes which are ultra low energy, which you're not supposed to do in Wilson RG, but sometimes you have no choice. You always end up generating mod omega term. I mean, some non-analytic term. So, but anyway, yeah, I don't want to stretch on this, but can I ask one more question? I think there's so many questions. Let me just stop. I think I will catch up later. Thank you.
Actually, I have a comment on Taron's question. I don't want to barge in, but I have a comment on this or follow up?
Yes, please, go ahead.
Yeah, so Taron, I think he's correct. He said you can generate a mod omega term, but these non-analytic terms were non-analytic in phi, but you can also generate that from fermions. Because of the Fermi surface, you generate non-analytic terms in phi, and that's why you can get first order transitions in Hertz-Millis theory of ferromagnets. So you can generate it in equilibrium. But I'm a bit surprised if you understand how you generate it here, because to my understanding, although you have non-equilibrium baths, the baths themselves are just like white noise. They're just finite temperature baths. There is nothing critical about them, unlike fermions, which have a sharp Fermi surface. So I sort of understand why we can generate non-analytic terms. Do you understand kind of beyond cranking the RG, how exactly these are generated and why non-equilibrium is important here?
Yes, I don't know if you can still hear me, but we're basically looking, so basically in this self-consistent equation, it involves let's call them the hybridization function that basically involves the spectra of these two baths. And because we're looking at critical physics, because we want to look at phi close to 0, basically, we're going to look at the low energy features of this spectra, and they can be anything. They can, as a spectra, I say, free electrons in 3D. They would start with a power law, right? A power law with a non-integer power, and this is a non-analyticity.
No, I don't understand, but it's finite temperature. There is no non-analyticities in classical spectra at finite temperature.
No. The spectrum, the density of state, does not depend on temperature. For free electrons, it does not depend on temperature, correct?
But I could write Langevin equations for this. Why do I need to know any dynamics for this?
No, you're talking to a bath and you're exchanging energy with the bath. Maybe this bath is at 0 temperature, fine. The spectrum of the bath will change your dynamics, correct? Depending whether there is room for you to borrow and there's a state for you to borrow energy or not. So, and this information is going to be encoded in this hybridization function U, right, which is basically the spectrum of the bath. And the spectrum of the bath, if you take some electrons in 3D, I don't remember.
It's always smoothed by the temperature, by the, let's say, Fermi function or something.
Temperature
Yeah.
it's not in the spectrum. Spectrum is on the number of states that are available to you at given energy. Right?
Okay, there are many more questions. I'll leave it here. Yeah.
So Anusha, you want to ask next?
Oh, yeah, sure. I just had a quick question about whether, is coarsening physics important at all in qualitatively in anything that was shown up in the modify, and maybe or just related, what would be the effect of having a symmetry breaking field around? Like, does that dramatically change the free energy profile here?
All right, thanks. So for the first question was whether, well, so we rely indeed on all the results that were we rely on all the things that we know about coarsening physics. We rely on the fact. So I didn't show you the computations, but we rely on the fact that you have domains that are growing at a speed square root of time. We rely on many things that we know about coarsening phenomena. If you add, I don't know, if you want to add some, so if you want to add some symmetry, so you want to add, for instance, a magnetic field on top of the Ising model. So that I don't know how it will develop, but typically I think it could probably be computed. I cannot really comment on what's going to happen exactly. Yeah.
Okay, maybe Michael, you want to go on, and then Sebastian, and then we stop because otherwise it will go very late. So Michael, please.
Sounds good. Thank you. I feel like I'm missing something very basic, which is you have this T critical that you're writing down for the non-equilibrium steady state. But then if I look at your free energy landscape, there's no symmetry breaking. It's still phi equals 0 is the minimum. So can you help me understand what exactly is the phase transition here?
Yeah, that's a very good remark. So indeed. All right. So because of this stochastic reheating, you're effectively restoring the Z2 symmetry. Right. So it means that independently of the temperature, independently of the dimensionality of your system, you are going to have some Z2 symmetric solution. So, and the only solution is phi equal to 0. So in some sense, before doing any computation, you know that this reheating procedure is going to be very strong on the non-equilibrium fixed point, because you know it's going to destabilize the IR physics, because you know that there's only one global minima, which is phi equal to 0. So that's why when I showed some potentials, I should probably say again. When I shoot some potential here, indeed there is, you can stare at it, there is only one single minimum, which is at phi equal to 0. So does that mean that there is only one phase in that model? And I think the answer is no. So even though the magnetization or a parameter is not able to distinguish the two phases, you still have two phases, because you see here you are basically in a situation where after so you have some reheating event, and after some reheating event, you're going to have some coarse graining physics with bubbles growing, etc., etc. And if you do some 2-point measurement, you will see this. Whether in that phase, in the paramagnetic phase, in the presence of reheating, you are, whatever you do, you are really at the paramagnetic fixed point, and even 2-point measurement will confirm that you are in the paramagnetic. So what I'm saying is that the static measurement of the fluctuation of the magnetization will not be able to tell you which phase you are in. The full potential tells you this, But if you want to have some information about your phase, you should probably look at 2-point measurement, two-point function times.
Okay. And just quickly, while you have this figure up, should I also interpret this literally that below the critical point there's a metastable symmetry breaking point there?
You mean?
Yeah.
Yes.
Okay. Thank you.
So Sebastian, please.
So following on Tarun and Ehud, I mean, I was wondering how that relates to this Coleman-Weinberg phenomenon. And so that's also something you can have at equilibrium whenever some order parameter field is coupled to some other low energy degree of freedom. For example, a superconductor where you couple the order parameter to a gauge field. That also gives you kind of these deformations with cusps, so of your potential landscape. And then the physics consequence often is that you have a first order fluctuation induced first order transition. So I'm wondering a bit how that compares and whether, I mean, your transition actually, when I look at this potential at the cusp, so I don't see really low energy mode. So would these transitions be first order or?
Yeah, I just want to reemphasize again that I'm not doing, I'm not selecting some crazy bath. I'm not selecting something that has Goldstone bosons or anything low energy. I'm selecting the simplest baths, but all the baths at the end of the day, if you look at them at low energy, they are going to have some power law, right? Typically, and they can bring in non-analyticity. And maybe I should have also emphasized the second thing is that if you look at this self-consistent equation, all right, non-analyticity can come from the power laws of this density of states of the hybridization function at low energy. But they also come from the fact that you have already these absolute values here of phi upstairs and below, which already are bringing you some non-analyticity even before you go into engineering your band, basically.
But about the nature of the transition, I mean, more the operational side of it. I mean, the consequence is these transitions first order or?
Here, well, you see here.
Because I mean, just the pictures. Yeah, when I see this, there's this cusp, and then you have these two other kind of local minima around. So that looks to me a bit like.
As soon as you put a tiny little bit of reheating, so the thing that controls this reheating is the rate R. As soon as you put R finite, basically you go from your ferromagnetic solution to a paramagnetic phi equal to 0 solution, right? So it's a brutal transition.
Thank you.
Okay, so thank you very much, Camille. Thank you again.